What's up, pre-calculus students? Mr. Messner, forgot my slate. Let's do this. So we're going to use our calculators to get some approximations here. We're going to solve some equations. It's going to be a lot of fun. Here we go. We got an equation already given to us, which is nice. There are some questions where we're going to have to provide the equation. It says the number of farms in Iowa can be modeled by this, where T is the number of years since 1980. Has the number of farms been increasing or decreasing since 1980? Justify your reasoning. Well, if you like graph this, or if you think about okay, I'm taking 0.987 multiplying it by 119, that number is going to decrease. So this is a decay situation. So it's decreasing. Why? Because 0.987 times any number will just shrink the number. We're taking a percentage of the original number. It's less than 1. That's why it's a decay. Find the number of farms in the year 1980. Well, 1980 is year 0, so it's 119,000. So f of 0 is 119 times 0.987 to the 0. So we started with 119,000 farms, but then 20 years later, we're going to have less. So 20 years when t is 20, what is this? Break out your calculator. 119 times 0.987 to the 20th. Only 91.598. We like to round things to whole numbers sometimes, but it's always safe. In calculus land, we round or truncate to the third decimal place. So that would be the amount. According to the model, in what year was the number of farms? About 80,000. So when do we have 80,000 farms? F of t is the farms, t is the years. So it's when the y is 80. All right, so we set up this equation. Now we have to solve. Okay, so this is equations that we've been doing last class. We got to get rid of this 0.987. We got to solve for t. Before we get rid of this, we got to get rid of this. You can't multiply these two things together. Don't do that. Instead, just divide by 119. You get 80 over 119 equals 0.987 to the t. You can find out what this number is if you want to, but whatever, we'll do it in a second. How do I solve for t here? It's 0.987. Well, guess what? There's a log base 0.987 that you can take of both sides. Log 0.987, base 0.987 of this is just going to cancel, leaving you with t equals log 0.987 of 80 over 119. Let's just do that. 80 over 119. Math, we got log base. It's easy to use, so let's use it. 0.987 of this number. You get about 30 years. Okay, but you can get a specific number, 30.346 or 30.347. Rounding, truncating, doesn't matter. In AP calculus land, you're allowed to round or truncate. I always recommend to truncate. It's easier. You don't have to do anything. 0.346. Truncating means read off the first 3 decimals and then just stop. Your visual near point is the closest point at which your eyes can see an object distinctly. The diagram shows the near point, y centimeters, at age x in years. So when you're 20, you can see an object distinctly 12 centimeters away from it. But me, not being 20, I have to be further back. It's the whole reading glasses thing. Why do we need reading glasses? When you're 60, you want to be able to read a book, but you can't distinctly see it I guess that's the reason. But anyways, you get an equation. Great. Use a model to project the visual near point for age 10. So when t is 10, when x is 10, we're talking about at age years. So, okay, y equals 3.5, 1.054 to the 10th. 3.5 times 1.054 to the 10th. Should be able to see something from like 5 centimeters away, 5.922. What age does the model predict a visual near point of 22 centimeters? Well, obviously, it's between 30 and 40, right? If we get this diagram between 30 and 40. So I'm thinking it's closer to 40 than 30. Let's see what this formula says. When y is 22 and the centimeters are 22, 3.5, 1.054 to the x. And you solve this similar to this one. You're going to divide by 3.5. 22 over 3.5 equals 1.054 to the x. How do you solve for this? Log base 1.054. Of both sides, you get x equals log 1.054 of 22 over 3.5. Let's type that into our calculator. I'll do it all at once. Math up, log base 1.054 of 22 over 3.5. Enter. 34 years. Oh, okay, so it's an exponential growth. Duh, Mr. Messer. It's not going to be like exactly in between. So it's rapidly increasing. So it's not closer to 40. It ends up being closer to 30. So about 34.953 years. Next, you plant a sunflower seedling in your garden. We got a logistic function. There's logistic functions and differential equations you have to solve in calculus. Logistics look like this versus exponentials go like this. More realistic, certain situations realistic to the real world. Find the time it takes the sunflower seedling to reach a height of 200 centimeters. So h is 200 centimeters after t time years. So we have to solve this equation. That's a 13, not a B. How do you solve this equation? Well, like we talked about this last video. If you got a fraction, get everything onto one level. So multiply both sides by this denominator. So I got 200 times 1 plus 13 e to the negative 0.65 t equals 256. What do I do now? Like, you could distribute the 200 if you wanted to. I'm going to divide by the 200 right away just because I think it'll be a little bit easier if I divide by the 200. Distribution would have been fine, though. And most of you will be more comfortable with like 256 over 200 plugged into your calculator. Whatever, there's that number, 1.28. Subtract 1.28. So I get 13 e to the negative 0.65 t equals 0.28. Divide by 13. Is that number? Don't lose that number. Billy, don't lose that number. Any Phil Collins fans out there? I'm going to put ... after that, knowing that it's not just that. Don't round, don't truncate until we get our final answer. All right, I'm ready to solve for at least the numerator by getting rid of the e. You You get rid of the e to the power by taking the natural log, the log base e of both sides. You get negative 0.65t equals the natural log of that number. Negative 0.3873, negative 3.837. Numerical dyslexia is a real thing. Putting a dot, dot, dot to know that there's more there. Divide by negative 0.65. And we get 5.904 years. Years? Not years. Weeks. Weeks. The Georgia River, herd of caribou in Canada. This is nice. Was estimated to be about 4,700 in 1954. Grew at an exponential rate to about 472,000 in 1984. That's a lot of caribou. Use the exponential growth function, P of t equals P naught e to the kt, where P naught is the initial population, and P of t is the population times t, to determine k. All right, so I start with P of t equals, I started with 4,700, so that's P naught e to the kt. We're going to find k by using this data. So 54 to 84, that's 30 years. So when t was 30, not 300, there's a total of P of 30 was 472,000. Now, if you want to make this a little bit easier, though, I know you guys aren't comfortable doing this. You can make this 4.7 thousands, and then this is 472. But let's not freak out, okay? Let's just want to just keep it there because you know you like it better. So we already have this initial, but this is what we're going to use to find k. Watch how this works. 472,000 equals 4,700 times e to this exponential growth constant times 30 years. Okay, we end up taking this 472,000, 427,000. Numerical dyslexia is a real thing. Over 4,700, you get this number. So I divided by 4,700 on both sides. 90.851, dot, dot, dot. I got e to the k times 30. I'm ready to bring down the k times 30, take the natural log of both sides. The natural log of this number is 4.509, dot, 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 equals 30 times k, k times 30, whatever. Divide by 30, you get k equals this divided by 30. 0.150. That is the exponential growth constant. We're going to use that, I guess, maybe in another part. During what year would the population have doubled its original number? Okay, so we have k now. So we have the formula for the amount of caribou by the George River up in Canada. It's 4,700 e to the 0.150. I don't want to round that number, so I'm just going to put that dot, 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 t. What is it going to double its original number? The original number is 4,700, so we want double that. When do I get double that? 9,400. Okay, this is not a like graph and see. This is a, we can solve an equation and find an exact number. So 9,400 is the amount of caribou. We're going to find t, the year. 4,700 e to the 0.150 dot, 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 t. I'm going to divide these two numbers. It's going to be 2. You're going to take the natural log of both sides. giving me ln2. Take that number. It's equal to 0.150 dot 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 t divided by that 0.150 number. So I'm going to take that number, divide it by this 0.150 exponential growth constant. And I get, after 4 years, so if we started in 54, we're talking about 58. We've already doubled. Man, that's a lot of caribou meat. If the herd had continued to grow at the same rate, what would its population have been in 2010? Is this realistic? Why or why not? It's not realistic. I'm just going to tell you right now. Things, including human beings, populations can't grow exponentially because then you're just going to continue to get like millions and billions and trillions of caribou. And guess what? The caribou are going to run out of food and they won't be able to sustain that population. Even if there's no hunters, and I know you guys love hunting caribou, but even if there's no hunters, there would just be eventually a limited amount of resources. There would be what's called a carrying capacity, a maximum amount of caribou. Let's see, though, if there was no carrying capacity, if the caribou had infinite space and infinite food, what would their population be in 2010? So let's see. 2010 is 56 years. Okay. 56 years. Here we go. P of 56, the population of caribou. 56th year, using this caribou exponential growth function, is, drum roll please, 4,700 e to the, this number, times 56, drum roll, to 21 million. It's 21 million. 21,264,110 caribou. Is this realistic? No. There's not enough space / food in Canada. No, there's a lot of space in Canada. You could say there's not infinite space, food, etc. There would be a max. It would be a logistic growth rather than an exponential growth. We got wolves. We got this formula. P of 0 is 500. Find P of t in terms of t and k. Okay, it just says like plug in 500. It appears that the wolf population is shrinking as it's 800 minus this. But I don't know. This is funky with the negative k. We'll figure it out. No, I think it's definitely shrinking, but maybe it's shrinking at a decreasing rate. So it's shrinking, but quicker than slower. So the wolves won't die out. So we got 500 e to the negative k t. All right, great. That's it. To show that though, like it might not be obvious that P naught is 500. If I plugged in 500 for P of t, I plugged in 0 for t, I get P of 0 e to the 0. E to the 0 is 1. P of 0 is not 500. Never mind. I get 500 equals 800 minus P of 0. P of 0 is 300. So my formula so far is 800 minus 300. That's how you get the P of 0 is 500. My bad. E to the negative k t. Now we're going to find k using this point, 2, 700. So 700 for P of t equals 800 minus 300 e to the negative k. Negative k is just like the exponential growth constant times 2. We'll solve by isolating the e to the power, take the natural log of both sides, divide by negative 2. So subtract the 800. I get negative 100 equals negative 300 e to the negative k times 2. I'll divide by the negative 300. I get positive 1/3. That's easy enough to do. E to the negative k times 2. I'll take the natural log of both sides. I get the natural log of 1/3 equals negative k times 2. Obviously, it's like negative 1 times k times 2, and you can multiply anything in any order, so that negative can go in front of the negative 2, and then I can divide by negative 2. So the answer is log of 1/3 divided by negative 2. And let's see what k is. Log of 1/3. I'll show you something interesting, though, in a second. Instead of using this decimal, I might have been able to do this for the last problem. It's this number, but watch this. Watch this. If I plug that in, first of all, we know like log properties. You can rewrite this as negative 1/2 log 1/3. And you can move this up to be log of 1/3 to the negative 1/2. Negative power is just the reciprocal of the positive power. So this would be 3 to the positive 1/2. So log 3 to the half. So I got 800 minus 300 e to the negative k. I could have just solved for negative k, to be honest, but whatever. I should have solved for negative k, honestly. Make that a positive. Make that a negative. Make that a positive. Negative k is equal to log of 1/3 to the 1/2. Okay, e to the log 1/3 to the 1/2 t. Now, if this was the decimal, that's fine. You would leave it. But watch what I can do here. You might not want to do this, actually. You could rewrite this using exponential properties. E to the log 1/3 to the 1/2 turns into 1/3 to the 1/2. But then you'd have to multiply by e to the t. Never mind. Never mind. Never mind. We got k. It's this number. Why don't we just use that number? It's negative k, so it's negative 0.549. Dot, 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 t. Using a and b, find p of t in terms of t. Then find the inverse of p of t. So we want to solve this for t. So it's like, how can I find the amount of wolves if I have a population of wolves, how many years would it take us to get there? That's kind of what we're doing. E to the negative 549 dot, 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 t. So I want to solve for p of t. I want to solve for t here. So it's just like, if I had this, how would I solve for t? I would subtract 800, divide by negative 300, take the natural log of both sides, then divide by negative 0.549. Let's just go one step at a time. I subtract 800. I divide by negative 300. I take the natural log of both sides. And then divide by that. So this is how you find the years based on that. Find the inverse of P of T. I feel like that is the inverse of P of T. Inverse is when you flip flop the variables and then solve for the other one. Like if this is X and this is Y, you would solve for Y. This is the inverse. So I don't know if there's anything more to that. Don't stress about it. It's not that important. Okay, this is like the same thing. So we have a money situation, compounding situation. I always use the formula: the future value is equal to a present value times 1 plus the rate divided by the compounding. Sometimes I use K for compounding. To the compounding amount times the amount of years. If we're being compounded continuously, K is infinity. And when K is infinity, this turns into E. That's where E comes from. You ever want to do something fun? Type in to your calculator 1 plus 1 over a very large number. So type in a huge number. Like make sure you know what that number is. And then to the same huge number, I'll show you. That's where E comes from. So that's why we use the formula P equals E, P times E to the RT for continuous compounding. That's why E shows up so much in math. It's because it's talking about infinities. And in math, we use infinities a lot. So 1 plus 1 over, I'm going to use the big number 987,654,3210 to the 987,654,3210. Watch. What's that number? Very, very close to E. Okay, if I used a bigger number here, closer and closer to infinity, we'll see it's going to get closer and closer to that E. I feel like I should have been closer to that, but whatever. Anyways, so this formula, since it's continuous compounding, K is infinity, turns into like my future amount equals our present amount, E to the RT. R is the rate at which we are continuously compounding. 6.25 interest is 0.0625 as a rate. We have a initial deposit of $1,000, E to the 0.0625 T. I'm going to find the inverse. So again, this is like solving for T. So you can see how many years it would take to get a certain amount. So double your money and stuff like that. So you got your future value that you're going to divide by 1,000. That equals E to the 0.0625 T. You're going to take the natural log of both sides, future value divided by 1,000. And you got 0.0625 T. You're going to divide by 0.0625. And that's the inverse. That's how we can find a time given a amount that we're looking for. So like how long will it take me to double this, to grow this to $50,000? You plug 50,000 into future value divided by 1,000. Take the natural log of that divided by 0.0625. You get the amount of years. All right, so this is that type of question. Similar, only we're going to find the actual amount of years. So Elena deposited $2,250 into an account that pays 6% annual interest, compounded monthly. Find the number of years it takes for the balance to reach 2,500. There you go. Divide by 2,250. Take the log base, whatever this number is. What's that number? We'll figure it out. Then divide by 12 and get your answer. So 2,500. I'm going to just show all the steps and then we'll type it into our calculator. Actually, might as well figure out this number. 1 point, sorry. 0.06 divided by 12 plus 1, 1.005. So 1.005 to the 12t. And take the log base 1.005 of both sides. Gone, gone, gone. You guys are more comfortable with numbers than like writing everything out. So 2,500 divided by 2,250. Log base 1.005 of that number is 21.1247 dot 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 equals 12t. Divide that by 12. It'll take us about 1.76 years. 1.760 years. Half-life. There's a half-life formula where it's like initial amount, present value. Present value times 1/2 to the amount of days or years or whatever divided by how long it takes for it to be a half of its initial thing. So it's like if the half-life is 3.8 days, this becomes 3.8. And you can see like if t is 3.8, I'd have my initial amount times a half. I'd end up with half of what I started with. And this is how we're going to get like our future amount. We got a 16 milligram sample. We're talking about 7.6 days. That's double the half-life, right? So it's like half-life 3.8. Well, then I'm going to take a half of that again. It's going to end up being a quarter. But let me show you. My future amount equals my initial amount times 1/2 to the 7.6 over 3.8. Like this is just 1/2 squared, which is 1/4. So this will just be 4. I don't have to do that. Should do that just to check. 7.6 divided by 3.8 is 2. Good. 1/2 squared is a quarter times 16, 4. How many days will it take until this 16-gram sample turns into 2 milligrams? Well, like you could kind of figure this out without using, I think you can figure this out. So let's take half of 16. Yeah. So 16 goes to 8 after 3.8 days. I'm going to give you a tougher one. 16 goes to 8. Eight after 3.8 days. It's important. Like if you understand this, like that helps. 8 goes to 4 after 7.6 days. 4 goes to 2 after 7.6 plus 3.8, whatever that is. 11 point something. 11.4. That's the answer. Now, we get it that way. Here's the other way to get it. When is our future value 2, starting with 16, 1/2 to the t over 3.8. You're going to take 2 divided by 16. It's 1/8. You're going to take the log base a half of both sides. I only did it the other way because it worked out so nicely. If it ever doesn't work out and it's like a random number, you got to do it this way. This ends up being -3, right? Log base a half of 1/8 Did I say negative 3? 3. That equals T over 3.8 multiplied by 3.8. That's what we just did. 11.4. 9, 10. 2 more questions. Stock price at $40 increases at a rate of 8% per year, not compounded. Thank goodness. Man, jump on this if you ever see something that's guaranteed to increase 8% per year. Oh, man. Put all of your money into that stock. All right, so my future value of my stock price is equal to my initial value, 1 plus my rate to the t. No compounding, no worries. Find the inverse of the function that I wrote. So the inverse is like solving for t. So I got 1.08. So I'll take my future value, my y, I'll divide it by 40. That's equal to 1.08 to the t. I'll take the log base 1.08 of both sides. I'll get log base 1.08 of my future value over 40 is equal to t. So this is how we'll find years. Use the function we wrote in B to find the number of years it'll take for the stock to reach 50. So when the stock price is 50, we'll find t by plugging it into that. It's the same, like, honestly, this is more of like in science, we always like to solve for the variable that we end up looking for. It's very important in computer science too, to have an equation set up so that it's solved for the variable. That way you can just you can plug in like a lot of numbers and it just spouts it out rather than like solving every single time. So it is an important thing, but in math, we love solving equations, so don't have to have it. So it's the same as like solving this equation. Right, you divide by 40, take the log base 1.08. But let's plug this into our calculator. Honestly, I think it's easier to use the change of basis sometimes. Log of 50 over 40 divided by the log of 1.08. That's easier to type into the calculator, I think, sometimes. 2.899, don't believe me, math log base 1.08. 50 over 40 is the same as 5 over 4. Okay, so in 2.89, what's going on? Go away. Oh, man. 2.899 years. And what's that increase? .25%. Only takes 2.899 years, and you get 25% richer. One of many byproducts of uranium is a radioactive plutonium. I feel like we're in Back to the Future here. Plutonium. Anybody watch Back to the Future? You should. Gets better and better the older you get. I'll tell you why later. Has a half-life of 25,000 years. Yikes. If some of this plutonium is encased in concrete, what percent of it will remain after 100 years? This is the whole nuclear power. It's what was the show? Chernobyl on HBO. That's a messed up show. But that actually happened in real life. Shows all the uranium that just got out into the world. It's very, very toxic for the rest of humanity. What percent? So the percent is the question. An easy thing to do is just say let's say we had one thing of plutonium to start. Okay, so that's my present value. So my future value is what percent of one. So whatever number I get will be a percent if one is 100%, right? You could also use 100, and that's fine. So 1/2 to the T over 25,000. I feel like we're making a political statement here. If we have 100 years, .5 to the 100 over 25,000. So 99.7%. So it just shows you it's never going away and it's going to be radioactive. You can send it to the moon, send it to space maybe. All right, that was fun. Some of these real world problems are fun. Hope you enjoyed. Mr. Messer out.